Good afternoon. So, let us continue with our discussion of CVD processes. In the last couple of lectures, we have talked about the thermodynamic and transport aspects of CVD film formation. And so, we will now discuss in some detail aspects about the structure of CVD films and their properties, probably in the next couple of lectures. And then we will talk about methods of measurements that are used to characterize these properties of CVD films. Before we do that, one quick correction. I think in the last lecture I was talking about the formula for the boundary layer thickness. I do not know if you caught it or not, but I think I made a mistake. The boundary layer thickness is 5 times square root of it should be nu times x divided by u infinity, where nu is the kinematic viscosity and x is the downstream distance and u infinity is the approach velocity. I believe I had not written it correctly. So, just make this correction. Dimensionally it checks out, and also the thing that bothered me even the other day, it just at the back of my mind, is that as the velocity increases, the boundary layer thickness should decrease. So, this formula has the right qualitative dependence, and so just make this correction in your notes. Okay, so talking about CVD films and structures, again there are two ways in which we can classify CVD films. The first is based on their functionality, the second is based on their actual structure. Now, based on functionality, CVD films can be simply classified as semiconductors, conductors and insulators or dielectrics. All three types of films can be formed on surfaces, and the substrate itself again can be conducting or insulating or semiconducting. Now, in terms of structure, as we have briefly stated earlier, the three types of CVD film structures that you can achieve are the amorphous structure, the polycrystalline structure and the crystalline or single crystal structure. Basically, as you go from amorphous to polycrystalline to single crystal, the order of the structure keeps increasing, and you get a very precise crystalline structure when you talk about single crystal films, whereas an amorphous film can have very little structure essentially. And there are ways in which you can control the CVD process to achieve these films, and we will talk about that a little bit. The other aspect of CVD films that we need to be aware of is the actual sequence in which they form. When you deposit a CVD film on a surface, it does not immediately form as a smooth, continuous, uniform film. There are actually 4 stages in the formation of a CVD film, and these are: first you have a nucleation step, the second stage is called nuclear growth, the third stage is called island coalescence, and the fourth and final stage is where bulk film forms. As the name suggests, initially what you form are these isolated nuclei on the substrate, which happens essentially because of heterogeneous nucleation as the vapor phase comes in contact with the energized solid substrate. These nuclei are likely to be of the order of a few angstroms or tens of angstroms. As more deposition happens, eventually these nuclei start to become larger as they absorb more vapors that are depositing onto the surface. So, that is the second stage. it is a transition stage where you still have not really formed a film. These are still isolated locations where the condensate exists. The third stage, island coalescence, is where a few of these start finding each other as they grow large enough and forming these islands, which is still not a continuous film, but now you are starting to form clusters of molecules attaching together to form these isolated and very, very short films. Finally, the bulk film stage is where these islands start to coalesce together and you eventually wind up with a nice continuous contiguous film. Now, if you look at what is happening at each of these stages and what are the barriers, the first stage, nucleation, is actually pretty much controlled by the vapor phase processes, the transport processes that bring the molecules to the surface, as well as the heterogeneous equilibrium at the solid surface. Does the surface promote the formation of these initial nuclei? So, that very much depends upon whether the surface is sufficiently energized to promote the formation of the nuclei. If the surface energy conditions are such that the formation of these nuclei is thermodynamically and kinetically favored, then these first droplets will start appearing on the surface. But at that stage, it is not a stable film. These nuclei are just as capable of reversing and re-evaporating. The second stage of nuclei growth happens when there is sustained arrival of vapors onto the substrate. So, you need to have a vapor deposition rate that is sufficient and sustained, so that the droplets do not re-evaporate and enter the vapor phase, but rather more and more material accumulates on the surfaces of the nucleated droplets and the droplets start growing. The third stage actually requires that these droplets kind of find each other. So, they have to be sufficiently mobile on the surface, so that they can find the nearest neighbor, get attracted to the nearest neighbor and form these so called islands or clusters. What that requires is that surface diffusion processes must also be promoted by the prevailing conditions of the substrate. Again, it is primarily an energy issue. If the molecules are sufficiently energized when they strike the surface, they will have a tendency to migrate on the surface, and eventually they will find each other and form a continuous film. On the other hand, if as the molecules arrive on the surface, they are not at a sufficiently high energy state to be able to move around on the surface, they may never find the nearest neighbor. So, the isolated nuclei may stay as isolated nuclei. So, at the third stage, the propensity of the surface to allow migration becomes important, and finally, the fourth stage is actually what you see as a product, the continuous film. Some of the other properties of the substrate that play a role in this are, for example, surface energy, hydrophobicity, hydrophilicity. Does the surface accommodate the arriving material and allow it to form droplets? For example, if you have a very low surface energy surface, it will actually repel arriving molecules. Nothing will stick. You remember the sticking coefficient we talked about? The sticking coefficient is a direct has a direct dependency on surface energy. The higher the surface energy, the greater will be the sticking coefficient. If you have an extremely low energy surface, for example, if you try to do CVD on Teflon, very difficult to make it happen unless you pre-energize the Teflon by bombarding it with plasma or ions or laser or something. But as it is, Teflon is an example of a very low surface energy surface which will not easily accommodate arriving vapor molecules. So, surface energy, wettability of the surface, how easy is it to form a continuous film on the surface, or is it going to keep breaking up? So, even after you get past stage 3 and you are trying to get to stage 4, is this transition again thermodynamically favored? So, there are a lot of issues that affect each of these steps in the process. and you really have to, in order to get a nice smooth continuous CVD film on the surface, what this points out is that there are several aspects of not only the gas phase, but also the solid substrate that must be controlled and optimized in order to make this happen. But suppose we have succeeded in making a CVD film on a surface, then we have to start looking at the properties of the CVD film and whether they satisfy our specifications or requirements. So, when you talk about CVD film properties, you can actually classify them into two categories. One is functional and the other is physico-chemical. Of course, the physico-chemical properties of the film actually deliver its functional properties. So, there is a linkage between the two, but when you deposit a film as a product, what you are really interested in is its functional properties. Does it do the job that it is supposed to do? If you have deposited the CVD film in order to achieve a certain conductivity, let us say, have you achieved that conductivity? Or if you have deposited the film to achieve a certain hardness on a surface, if it is a coating for example, have you achieved that hardness? So, the functional properties vary depending on the application. For every application that you have, there is a specific property or more of the CVD film that is appropriate. So, from a producer viewpoint and from a consumer viewpoint, these functional measurements are the most relevant, because they basically decide the quality of the film that you are receiving. However, in order to achieve that quality, in order to achieve that functional value, what we do is we try to control these in order that that happens. So, our direct controls are on these properties, whereas our direct effect is based on the functional properties of the film that we are achieving. So, what are some of the physico-chemical properties of a film that are important? Obviously, the thickness, and related to that the deposition rate, uniformity, and composition. These are what I would call first order effects. When you are designing a CVD process, these are the parameters that you focus on right away and try to set some specifications. What is the thickness range that you want to have? What is the rate at which you want the film to be forming? What is your specification on the uniformity? Do you need plus or minus 1 nanometer variation, or do you need plus or minus 1 micrometer variation over the surface? And the composition. What exactly should be the chemical state of the film that you are depositing on the surface? Now, if you look at these, we will talk in the next few classes about how to measure these things, but thickness of the film is obviously related to the deposition rate. Essentially, the higher the deposition rate, the greater is going to be the thickness. Uniformity, on the other hand, is not necessarily dependent on the deposition rate. You can have a very high deposition rate, but the uniformity may not be very good unless you have tight controls over how the substrate itself is prepared and presented to the CVD process. For example, if your substrate is has a lot of impurities on it, contaminants on it, that can affect the uniformity of your deposition process. So, depending on the local level of contamination on the surface, you may get a completely different type of film, different thickness, different deposition rate, and also it may depend on the features on your substrate. If you have a very flat and plain surface, the uniformity may be very good, but if you have a rough surface or one that has a lot of contours, the uniformity may be more difficult to achieve. So, uniformity provides actually a connect between the process of deposition and the process of film formation on the surface. So, related to the uniformity is what we would call step coverage. if your substrate has certain features on it, particularly steps, how well is the CVD film able to follow this step structure and provide uniform coating thickness everywhere. So, this step coverage is another important parameter when we are trying to characterize a CVD process. What are some of the other parameters that could be important? And by the way, when we talk about composition, the reason it is important is obviously because the composition decides the functionality. If you are trying to deposit a semiconductor, you want to see a semiconductor, silicon. You do not want to see silicon oxide, right, which is a dielectric. So, the controlling the composition is very important, but the composition is very sensitive to the process of CVD. For example, if you are trying to deposit silicon from silane, and if you are using hydrogen as a carrier gas, if an excess of hydrogen actually gets absorbed on the silicon, then you do not get a crystalline structure of silicon, you start getting amorphous silicon or polycrystalline silicon. Or in other cases, for example, if you have some impurity that enters your CVD reactor, for example, oxygen is frequently an impurity in CVD systems, because unless your CVD reactor is hermetically sealed, it is very difficult to prevent air from seeping in, which is mainly O2 and N2. N2 is relatively inert, so usually does not bother us, but oxygen, if it seeps in, can certainly affect the composition of your deposit. Another one is water. It is very difficult to keep moisture out of CVD chambers. So, oxygen and H2O are frequently contaminants that will enter your CVD system. Now, so what can happen in that case is, instead of forming silicon semiconductor films, you might start forming silicon oxide, right, or in case where the nitrogen gets absorbed, you can even form silicon nitride type of films, which are clearly what you do not want. So, the composition is a very important parameter to monitor and maintain records of, because it is an indicator of whether your system is performing as it is designed, or you are having impurities and contaminants enter the system. And even in cases where you are trying to make an oxide film, suppose your CVD film is going to be SiO2, even then the amount of gases can play a big role. For example, you want a stoichiometric SiO2, but if you have an excess of O2 in your system, you may form some SiXOY where the ratio of oxygen to silicon is higher than stoichiometric ratio, in which case the film that you deposit will not have the properties that you are looking for. So, the composition of the film has to be monitored, because it will give you a very sensitive indication of the functionality of the film. So, composition is one that we need to keep our eye on. So, what are some of the other properties? Grain size, particularly when the durability or integrity of the film is a very strict requirement, the grain size plays a huge role. You want to, in CVD processes, achieve as fine a grain size as possible mostly. So, you have to have some control over the grain size that you are achieving. Now, grain size is also related to the stress level on the film. When a film is subject to compressive or tensile stress, it can crack. So, the susceptibility of a film to cracking or other types of stress related disorders is very important to characterize as well. Now, what controls the stress level again is the grain size. The coarser the grain, the more likely it is that the film will be affected by various stresses that are present on the surface. A fine grained structure enables a much more robust film to be realized on the surface. Other things that may be of importance are smoothness or roughness of the film. When you do a morphology characterization in 3 dimensions, your requirement may be that the third dimension, which is a surface roughness profile, cannot exceed a certain value. You may have fairly tight standards on how smooth the film should be, in which case we have to use a technique like AFM to understand not only the 2-dimensional structure, but the 3-dimensional structure of the film, and ensure that the film roughness is below the specifications that we need for that particular product. What else? I mean, obviously things like hardness, density. Actually, another parameter that is frequently measured on CVD films is called the etch rate. So, what's done here is you take the film and expose it to hydrofluoric acid, and you measure the rate at which the film is being etched by hydrofluoric acid of a certain concentration. The rate of etch of the film is a very good indicator of how well integrated the film is on the surface. So, essentially the higher the etch rate, the less strongly adhered the film is to the surface. So, typically for any CVD film, depending on the application, there will be a specification on the allowable etch rate. So, the conditions will be specified: what acid to use, what concentration to use it at, how much time to be allowed for the etching, and then there will be a value given as to what is the maximum allowable etch rate. So, that is another very sensitive parameter of that reflects the quality of the CVD film, particularly in terms of surface integrity and so on. And in fact, another parameter that we need to look at is purity and integrity. Purity is essentially the level or concentration of impurities in the film. Integrity refers to how that purity changes as a function of the depth of the film. So, in other words, if you slice the film and you looked at the impurity levels at each cross section, the purity typically refers to the outermost layer. Integrity is a reflection of how well the impurities are contained throughout the thickness of the film. That is in terms of compositional or chemical integrity. Similarly, you can also talk about physical integrity, where some of these parameters that we are talking about, like hardness and density and so on, we can similarly slice the film and ensure that these values are maintained not only at the outermost layer of the surface, but throughout the bulk film. Okay. So, these are just some examples. I mean, there are many other parameters that you can measure. There is refractive index, and in fact, the thickness of a CVD film is measured using its refractive properties. And so, the refractive index is another one that is typically fairly high on the list of parameters that are measured. And of course, there are many other properties such as the depth and width profiling of the film, its ability to follow corners. So, the number of measurements that you can do to characterize the film in terms of physico-chemical properties is very large. Now, the reason that you want to do that, I mean, when we talk about functional properties, as I was mentioning, these could be simply electrical, mechanical and so on. These measurements are actually much easier usually. I mean, all you need to do to measure the conductivity of film is use a conductivity meter and measure its conductivity, right. And similarly, mechanical properties, if you want to measure its for example, its coating strength or whatever, you expose the surface with the film to high temperature, high humidity environments and see if corrosion happens. If it does not, then your coating is good. So, the functional measurements are actually easier to do, but the property measurements, the physico-chemical property measurements are important when you are first designing the process. when you are first setting up the process, you have to do the whole battery of tests in order to ensure that the process is set up the way it should be. But once the process is stable and running, you do not really need to do all these tests on a daily basis. What you would typically do for day to day quality control is do the functional tests and then some subset of this. For example, thickness is measured on a daily basis, but deposition rate is not, composition is not, because once you have set up a system, you do not expect composition to change on a daily basis. You probably will do a check say on a monthly basis just to make sure that some impurity has not entered into your system. But typically if the composition has changed, it will show up in your electrical or mechanical measurement. So, you do not really worry about it too much. So, for all these tests, the one that would be done most frequently would be the thickness and the etch rate test, and uniformity of course will be looked at as part of the thickness measurement. So, essentially when you do the thickness measurement, you do not do it at just one place, you randomly select several locations on your substrate and measure the film thickness, and that gives you an idea about how uniform the film is. Okay. So, we have taken a brief look at some of the properties of CVD films, and as I said in a couple of lectures down the road, we will talk in more detail about how to measure these properties. Let us switch gears now and again talk about the different types of films, particularly the single crystal films versus polycrystalline versus amorphous. We want to really focus on what are the different characteristics of these films, how do they differ, and what is common between them. So, single crystal films are also known as, does anybody know the other name for single crystal films? That is actually a Greek name. They are also called epitaxial films. Epitaxial in Greek literally means arranged upon. So, basically that is what it is. In an epitaxial film, you are taking the arriving material and arranging it on the substrate in such a way that you have a very precise crystalline structure at the end of the process. The most commonly realized film using epitaxial CVD is silicon, epitaxial silicon, but others are also used, germanium, even compounds like silicon germanium and so on. The substrate itself can also be of the same material or it can be of a different material. So, for example, when you put silicon on silicon, it is called homoepitaxial process, where the substrate and the film material are the same. Why would you want to do that? I mean, why would you want to put a silicon film on a silicon substrate? What do you gain? The reason you want to do that is bulk silicon that you can get in large quantities has properties that are very difficult to control, highly widely varying in every possible way. The composition could be varying, the crystalline structures could be varying. So, you cannot guarantee that the surface of a bulk silicon ingot has certain properties, but by depositing a very thin film on top of this silicon, you can now have a top layer that has a very precisely controlled crystalline structure that is sitting on top of this epitaxial, I mean on this silicon. So, essentially you are depositing epitaxial silicon on top of bulk silicon. Now, when we put silicon on silicon, if you deliver the silicon molecules to the silicon substrate with sufficient energy such that they move around on the surface and orient themselves according to the crystal structure of the substrate, that is when an epitaxial film happens. So, for example, if you have bulk silicon that has a 1-1-1 structure and you deliver these vapor molecules to the surface, and as they impinge on the substrate, they immediately orient themselves also in the same 1 1 1 crystalline configuration. Then you start building a structure on the substrate which exactly matches the crystalline structure of the substrate. That is how you get an epitaxial film, right. But what happens if you have, for example, if the silicon itself is not pure silicon, but it has been oxidized. So, you have a very thin oxide film on the surface, then the arriving molecules are not going to see a crystalline silicon structure to attach themselves to, right. So, instead they will be now trying to replicate the silicon oxide structure that they see on the surface. So, if there is a oxygen contamination on the surface which leads to the formation of an SiO2 on top of the silicon layer, then the film that results is going to be amorphous in nature, because it matches the surface that it is seeing. Or the other reason why this could happen is if you have again impurities or contaminants on the surface. Here again the vapor molecules that arrives at the substrate is not going to see crystalline silicon, it is going to see whatever contaminant is sitting on the surface. So, the molecules are going to orient themselves in accordance with the contaminant rather than in accordance with the basic underlying substrate material. So, the point is, if you are trying to make single crystal films, very important to have an oxide free surface, and it is very important to have an impurity free pristine surface. That is the only way that you can make a crystalline film happen. On the other hand, if you are trying to make a polycrystalline film or an amorphous film, then you can actually do it by allowing selective oxidation of the surface to happen, or by changing the composition of the surface in such a way that the arriving molecule will orient itself in an amorphous fashion or a polycrystalline fashion. Now, in an epitaxial silicon layer, one of the advantages of using CVD to form these films is that you can very easily dope the layer with other materials. For example, elements like phosphorus and boron are frequently used to lend additional properties to the CVD film. In a CVD system, it is very easy to incorporate these external elements into the film simply by introducing them as an additional reactant into the film, into the reactor. So, by just changing the inlet composition of the feed stream entering the reactor, you can achieve either a pure film, whether it is silicon or silica or whatever, or you can achieve a film which has certain dopants incorporated in it. So, a CVD reactor can essentially become a doping reactor in a sense. To make epitaxial silicon, the favored precursor is SiCl4, which is typically reacted with H2 to give Si solid plus HCl. The reason that silicon chloride is preferred is because it can be used in a high temperature reactor, which essentially means that you can have a high deposition rate and you can get a crystalline structure. Essentially, the higher the temperature, the more crystalline will be the structure of the film that you make. If on the other hand you use SiH4 and do the pyrolysis reaction, this reaction does not require temperatures that are as high as what you need to use for the SiCl4 reactor. This reaction will actually run at temperatures that are about 200 degrees lower than what you require for the SiCl4 reaction. Another possible way of making this is to use SiH2Cl2, which again will go to SiS plus 2HCl. The SiH2Cl2 process to break down into silicon also can be run at a lower temperature. So, this reaction is more suited for epitaxial silicon production, whereas these reactions lend themselves more to polycrystalline and amorphous structures. The SiCl4 reaction sequence actually has another benefit in that you can actually control the rate of formation of the film through both deposition and etching. It turns out that if you keep increasing the concentration of SiCl4, eventually the deposition process will stop and the silicon tetrachloride will actually start etching the film that is already on the surface. Now, that is interesting because it gives you a way of controlling the thickness now using two mechanisms. Instead of trying to control it only using the deposition mechanism, you can also now control it by using the etching mechanism. In fact, if you plot the film growth rate which is typically in micrometers per minute against the number of SiCl4 molecules as a function of as a fraction of total gas molecules, you can actually have a behavior where the deposition rate goes from positive to negative. In fact, the typical behavior looks like this. So, this is -1, -2, 1, 2, 3. This is somewhere around 0.3. So, what this is saying is as you keep increasing the amount of SiCl4 in your system, you can actually start etching a pre-existing film on the surface. And then as you keep lowering the amount of SiCl4, the deposition rate will turn positive and you will reach a certain maximum growth rate for a certain value of the SiCl4 concentration, and then again it will turn negative, and finally as the SiCl4 concentration goes to 0, the film growth rate will also go to 0. So, this process, if you are trying to home in on a certain growth rate, we can do it lot more sensitively using this system simply by treating the concentration of SiCl4 as a tunable parameter until you get exactly the growth value that you are looking for. That type of precision control is very difficult to achieve with the SiH4 and SiH2 Cl2 systems. So, when you are growing a crystalline film, obviously the most critical deliverable for the process is the crystalline structure of the film. So, you constantly have to be on the watch out for defects in the crystalline structure. So, what are the typical types of defects that you can get when you are trying to grow crystalline CVD films? Again, contamination, both particulate contamination as well as organic contamination or defects to look out for. Organic contamination is also known as haze. Basically, if you look at a CVD film and if it is heavily contaminated with organic materials, it will have a hazy appearance. You will not see a very sharp image. It is usually an indicator that you have organic vapor species that have been incorporated into the film as impurities and you have to get rid of them. But in terms of the structure, the major types of defects to look out for the first is what is known as spikes. When you are trying to grow a film, obviously you want an equal growth rate everywhere on the substrate. But what can happen is if you have certain types of impurities present at certain locations on the substrate, the growth rate at those locations will be much greater than at other locations. So, instead of seeing a nice uniform film like this, essentially you will see something that looks like that. You will see a sudden jump in the thickness of the film at some location. So, the structure may still be crystalline, but the uniformity of the film will be affected. So, that is the type of defect is known as a spike. The second type of defect is known as pattern shift. A pattern shift happens when the crystallinity itself is affected. For example, if your growth rate is too high, if your deposition rate is too large, then instead of growing in a single plane like it is supposed to, you may start growing a plane at a different angle just to accommodate the extra material that is coming in, or you might actually add another plane to your film which is not supposed to be there. So, these types of defects essentially lead to a change in the crystalline pattern of the film itself. So, these patterns can sometimes result in dislocations, they can result in the formation of an extra layer or extra plane of material and so on. They also have the habit of starting close to the substrate, but then propagating with their way through the film. So, it is once this type of defect starts, it becomes irreversible. So, eventually the defect will show up even at the outer surface of the film, even though the initial part of the defect formation was close to the substrate. Another type of defect that we see is slip. Slippage can occur between successive layers of the film, because when the CVD process happens, you are essentially putting down the CVD film one layer at a time, one molecular layer at a time, that is a few angstroms at a time. You are assuming that when the second layer deposits on top of the first layer, it is going to just settle down and stay, right, but that may not always be the case. There may actually be slippage between successive sections of the CVD film, so that the crystals are laterally shifted from one another, so that the uniformity of the structure may be okay in the horizontal direction along the film, but in the vertical direction across the thickness of the film you start seeing discontinuities in the crystalline structure. So, that is the other type of defect that we see, which we call slip defects. All of these defects obviously some of them can be fixed and some of them cannot. For example, something like a spike, if you see it, you can certainly take steps to address it by essentially taking the substrate out, cleaning it, putting it back in. Usually they will take care of it. Something like a pattern shift or a slip is more difficult to control, because that has to do more with the molecular behavior of the film itself. And the only way to address issues like this may be to either change your reactive conditions, change the species that you are using for the CVD process, or in some cases by essentially by introducing a post CVD step which can take care of these defects. For example, if you have a condition where the structure is not well aligned, you can actually do what is known as a post annealing step, which is essentially a high temperature baking. But what this does is it will provide sufficient energy to the molecules comprising the film that they will be imparted certain mobility, and essentially they will find the proper structure. They will kind of move around until the film settles down into its optimum form. So, annealing is a process which is frequently resorted to in order to improve the crystallinity of the CVD film. You can take a amorphous film or a poric crystalline film, and by doing a high temperature annealing process you can turn it into a crystalline film. But in addition, you can also take a crystalline film and improve its crystallinity and reduce its defects by doing thermal annealing. So, in any CVD process, supplying thermal energy to the substrate is always a good thing to do, unless the surface itself is prone to oxidation or other types of failure modes when it is exposed to high temperatures. And that is why if you look at CVD processes, particularly for achieving crystalline structures, they try to employ as high a temperature as possible. because it yields very high deposition rates. Film thicknesses can be achieved in a much shorter time, but in addition to all that, you can also have better quality of the film. The impurities can be reduced, some of these defects that we see can be eliminated, and in fact, if you have a surface in which some gases have been accidentally absorbed, as an impurity, H2 gas or O2 gas, again a high temperature process will enable you to desorb these gases and get them out of the CVD film quite effectively. So, wherever possible, if you are trying to achieve an epitaxial film on a substrate, try to use A, as few chemicals as possible, and B, as high a temperature as possible, so that you get a good structure and you minimize the potential for any impurities to get incorporated into the system. Now, in order to minimize impurities, essentially what that means is you want a system that is not open to the atmosphere. And in fact, most CVD systems that are used to get epitaxial materials are closed chambers with a very tightly controlled environment, quite expensive, and the production rates are typically small, but the product that is being made from these processes is also a high value product, and so people are willing to make the investment. On the other hand, amorphous and polycrystalline films, which we will talk about in more detail in the next class, are more likely to be laid down using atmospheric pressure and even open environment type of processes, because in those cases the impurities and the crystallinity of the film is not such a big factor, and mostly what you are looking at is maximizing the number of films that you can make per day and also the cost of the per film that you are trying to minimize. So, we will see that the design considerations for making polycrystalline and amorphous films are very different from the design considerations that we talked about today for making epitaxial films. Okay, so let us stop at this point. Do you have any questions?
So, the shelf life of the material, the properties you have discussed,
yes.
Shelf life also changes for the different types of metals.
True, but see that once you make the CVD film on a surface, it will typically get used in the next step of the process within a few hours usually, or at the most within a few days. I mean, you are not going to make a CVD film and put it on a shelf for months or years at a time. Typically, these are used for high production processes. Now, there are certain products like CVD coatings, which have to have a lifetime of the order of years. So, for those films, shelf life should not be an issue. But for semiconductor films, particularly those that are used in microelectronics, it can be an issue, but essentially as long as you are following first in first out principles and using the CVD surface as soon as possible, you should be okay. But that is where the measurements come in, that you have to, if you have made a CVD film and you are storing it for subsequent use, then you have to periodically go in and re-inspect it for its physical as well as chemical properties to make sure that they stay intact. So, I will see you on Friday.